Hello students, myself Swetha, Assistant Professor in the Department of Chemistry, and today we are just going to discuss about a determination of pKa of vinegar using pH sensor. Okay, so here vinegar we are going to estimate it today. Vinegar is to mean 10% acetic acid. The chemical name of vinegar is 10% acetic acid. And that acetic acid is a weak acid, and we all know that weak acid is a one that will undergo a partial dissociation when it is taken in the aqueous medium. So acetic acid, when it undergo a partial dissociation in the aqueous medium, the reaction we can look up like this. It is going to give you acetate ions and the H plus ions. As because there happens a partial dissociation, determination of pKa value will be a more important and a proficient way to determine its acidic nature. So therefore, we will focus on the dissociation constant which is present in pKa. And dissociation constant for any acid can be taken as the product of the molar concentration of the products to the molar concentration of the reactants, and this is what the mathematical equation we get. If this is a Ka there, how can we define pKa then? It is given by pKa will be equal to negative log to the base 10 of Ka. It is to mean that from this equation we can get the inference that in case if there is an increase in the value of Ka, definitely there will be decrease in the pKa value because there is a negative log to the base 10 term there, because of which pKa value will decrease. So with the decrease in the pKa value, we tell that more acidic the acid is. Even if it is a weak acid, the accurate acidic nature can be estimated by determining the pKa value for any acids. Okay. So therefore, to estimate this pKa value for the given acetic acid, which is commercially we call it as a vinegar, we have to go and do the titration. Against what? The same acetic acid will be titrated against NaOH. So when it is reacted with the NaOH, there happens neutralization reaction to give the salt and water. And the salt formed there is sodium acetate, and water will be the byproduct. And you should remember, this is what the acid which is present there, and this is what the salt which is formed there. So when you do the titration of this reaction, initially we can observe there will be the maximum concentration of the acid. When it is being neutralized with the strong base, the pH value gradually increases. But exactly at equivalence point, we observe that there is a sharp increase in the pH value of this titration reaction. Why? Because at exactly the equivalence point, we observe that there is no more vinegar available inside the reaction mixture. There will be purely NaOH. So therefore, there is a sharp increase in the pH value. And even after getting the equivalence point, one has to record 5 to 6 more readings, and there also there will be again increase in the pH of a solution because there exists a strong base which is NaOH. Okay, so if this is a reaction that will happen throughout the experiment process during the titration, in the sense one will have to record the pH value upon the every addition of this NaOH, and later on we will have to make use of Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation, it is given by pH is equal to pKa plus log to the base 10 of molar concentration of the salt to the acid. And here the salt is sodium acetate, and acid you all know that it is vinegar. Now we will consider the arbitrary situation, that if this is the acid which is present, before I start with the titration, let us consider its concentration to be the maximum, and we will say that its concentration is 100, that is acid concentration before I start with the titration. And what will be the concentration of the salt at that time? It is 0. So therefore the salt concentration I have taken it to be 0. And later on, once when I start with the titration, when it reaches the equivalence point, there is no more availability of that vinegar inside the reaction mixture, because all that vinegar, which is a 10% acetic acid, is completely converted into the respective salt. So therefore, the concentration of the acid there is 0, whereas the concentration of the salt goes to the maximum. So therefore, can we logically tell that exactly at the half equivalence point, the concentration of the salt and the concentration of the acid both are equal? Yes, definitely we can. So therefore, if this is a situation before the equivalence point and if this is a situation after the equivalence point, exactly at the half equivalence point, their concentration are equal. Now let us apply this situation here in the Henderson-Hasselbalch equation. So what is the concentration of the salt and acid there? They are equal, so they can be substituted over here. And as because they are equal to each other, they will cancel with each other, giving 1. And log 1 value is 0. So therefore, this whole term tends to 0. When that whole term tends to 0, we can definitely tell that whatever the pKa you are going to determine there will be itself the pH value. So if you can determine what is all the pH which you are going to record in the tabular column at the half equivalence point situation, whatever the pH you determine there is itself the pKa value. And now let us go and observe the demonstration of this experiment. The accessory that we need for this experimental determination include burette, pH meter, glass membrane electrode, beaker with a magnetic bead. Let's observe. This is how the experimental setup will look. It is going to contain a reagent bottle having weak acid for pKa, and there is also NaOH solution for the pKa estimation. There exists a digital pH meter, a magnetic stirrer, and there exists a beaker containing a magnetic bead. In this, 25 ml of the weak acid is taken from this. And now here in the burette, we have used standard NaOH. It is to mean that concentration is known to us. Now, we'll see the electrode which we use in the experiment. So this is a glass membrane electrode that we are going to use, and we can observe that there exists a glass tube and a glass membrane which is in the form of a glass bulb. This glass bulb is a one that is going to sense the concentration of H+ ions and will give the pH value through the digital pH meter. So therefore, while using this glass membrane electrode, you have to be very careful that the glass membrane is very thin and fragile and it may break any time. Even if it breaks, it doesn't produce a sound. So therefore, you have to use it carefully. Okay? And now, let us wash this electrode into the same beaker. Like this. And this beaker is replaced with our beaker which is containing weak acid. So be careful while replacing it. If that bulb touches the bottom of a beaker, it might break. So be careful while replacing this. To this weak acid, I am going to add 1 test tube full of demineralized water to create aqueous medium. And now let us switch on the instrument. So this initial pH is recorded in the tabular column. It is 3.5, and then exactly 0.5 ml of NaOH is added now. Upon the addition of 0.5 ml of sodium hydroxide, we can observe the pH value has increased. It has increased to 3.68. Let us record the reading likewise till we get the sharp increase in the pH value. Again add 0.5 ml. Wait for some time and note down the pH. And here we observe that there is a sudden jump in the pH value. Initially the value was 5.88 and now it has increased very sharply to 9.58. Let us record that and we call this reading as the equivalence point or jump in the pH value. After getting this jump value, just 5 or 6 readings one has to record. And now 5 to 6 readings are recorded. Now we can stop the titration. So let us switch off the instruments. Remove this electrode carefully and wash it into the same beaker. And then you can replace it with the beaker which was used earlier, like this. So this completes our experiment. Now let us use all these pH values which we have recorded during the experiment to calculate delta pH and delta pH by delta V. And using these readings, let us plot the graph in order to determine the equivalence point and half equivalence point which is required for the estimation of pKa value. Now let us see the observations and the calculations part. So once if we have recorded all these pH values, we will have to calculate delta pH, that is 3.68 minus 3.35, we will have to write it over here, and 3.92 minus 3.68 we will have to write it over here, and later on 4.23 minus 3.92 we will have to write it, and likewise for all the remaining readings one has to calibrate delta pH. After that, as we know that delta V value is 0.5 ml, use that value in delta pH by delta V calculations. You have delta pH, divide all those values by 0.5 and you will get delta pH by delta V, as shown here in the tabular column. Now let us use all those values in order to plot the graph. So here let us plot the first graph to calculate the equivalence point. So here we observe that we are going to make use of delta pH by delta V versus volume of NaOH. This is in terms of unit milliliters, and as pH is a unitless and a dimensionless quantity, we take up the SI unit only for the volume, which is per ml. Okay, we have 0.66 and a 0.5 ml of NaOH. Let's mark it 0.48, which is gonna come somewhere around here, and 0.62, 0.62, and 0.38, 0.38, 0.42, 0.42, 0.46, 46, 0.64, 1.44, which is around here, 1.44, and the next value we have is 7.38, which will come over here, and let us encircle that peak point as well. And then we have 2.44, which is somewhere around here, 1.76, 0.48, 0.52, 48 and 52. Now let us use the scale in order to join these peak points. So this is the peak point that we get. Just take a straight line to its next adjacent point, which is present there, like this. And on the other hand also, to the next adjacent point, take a straight line and you are going to get a peak like this. While for the other rest of the points which you have here, you can just join them in the free hand, like this. And you will have to take an extrapolation from this peak point towards the x-axis. Let that extrapolation be a dotted line, and you will mark this point over here and you will write it as equivalence point. And what is its value? It is exactly 4.5. So you will write 4.5 mm inside the brackets. And this is how you will estimate equivalence point. Now let us go and plot the other graph, which is pH versus volume of NaOH. As pH is again the unitless and dimensionless quantity, there is no units along the y-axis. So let us plot the first one. And we get the first point over here. Let us mark and encircle it. The next value is 3.68. So we'll mark over here and encircle it. And the next one is 3.92. That is at 1 ml. So 3.92. And the next is 4.42. So we'll mark it at 2 and we'll encircle it. And the next value is 4.63. So it is this one, 4.63. So we'll mark and encircle that also. 4.86 and 5.18. 5.18, 5.88, then the jump value, that is 9.57, 10.79, 11.67, 11.91, 12.17, and finally the last value. And this is what the points we have got. Let's join them using a scale. Here also, there are two farthest points and we will use scale to join them. Where the rest of the points, you can just join them in the free hand. And now you have got equivalence point, which is 4.5 ml. Half of it is 2.25, which is going to come somewhere around over here. And let's take an extrapolation till it reaches the curve. Like this. And as soon as it reaches the curve, take the extrapolation towards the y-axis like this. And we are going to mark this as half equivalence point. And its value is 2.25 ml, whereas over here we are just going to mark it as the pH, and the pH value there will be 4.8. So therefore we tell that at the half equivalence point situation, whatever the pH determined there is itself the pKa value, that is simply nothing but 4.8 value. So this completes the experiment. Now let us see the result. The first point is the equivalence point. The equivalence point value is 4.5 ml. The second point of the result is half equivalence point, which is 2.25 ml, whereas the pKa value for the given vinegar, which is simply equal to the pH value at the half equivalence, is 4.8. Thank you for watching. Happy learning.